This PowerPoint is about kinetic energy. Kinetic energy is the energy that is stored in motion. So we have lots of different types of energies we're going to be talking about in this unit. This one specifically is the energy due to an object's motion. So we're looking at an object's speed as it's going. So the equation for kinetic energy is 1/2 mass times speed squared. Change in kinetic energy is the final kinetic energy minus the initial kinetic energy. It's 1/2 mass times final velocity squared minus 1/2 mass times initial velocity squared. Just like any change, it's final minus initial, but the only thing that's going to be changing is going to be the velocity. So it's the final velocity here minus the initial velocity over here. And that gives us our change in kinetic energy. So a lot of times when we look at certain types of energies, we're going to be looking at a specific characteristic because we can't see energy, but we can see how it's manifested in certain ways. For example, kinetic energy will see a change in speed, and that change in speed indicates what whether the kinetic energy is increasing or decreasing. So if the speed is increasing, then the kinetic energy is increasing. If it's decreasing, then the kinetic energy is decreasing. A lot of times we're going to look at the magnitude of the velocity because the direction of the velocity doesn't make a difference with kinetic energy. Kinetic energy is a scalar, so we're just looking at the amount of speed or the amount of velocity as it's going through. In this example, it says a man with a mass of 88 kilograms is running at 18 meters per second. What's his kinetic energy? We'll simply put the kinetic energy equals 1/2 mass times velocity squared. So 1/2 times 88 times 18 squared gives me 14,300 joules of kinetic energy. In this problem, it says a plane has a mass of 180,000 kilograms and 1.41 times 10 to the 9th joules of kinetic energy. What's the plane's speed? So we use the equation kinetic energy equals 1/2 mass times velocity squared. Go ahead and plug in what we know is 1.41 times 10 to the 9th for the kinetic energy. And then half of 180,000 gives me 90,000. We divide both sides by 90,000. And then our speed squared is going to be equal to 15,700. So we go ahead and square root both sides. And that gives us our speed is going to be 125 meters per second. In this problem, it says a car of mass 3,500 kilograms is moving at 20 meters per second and slows down to 5 meters per second. What's the change in kinetic energy? Well, we know the change in kinetic energy is 1/2 mass times final velocity squared minus 1/2 mass times initial velocity squared. Your final kinetic energy minus your initial kinetic energy. Now, something I want to point out here is that we're starting at 20 meters per second going down to 5 meters per second. So since we're ending at a slower speed than what we started with, then we should expect a negative change in kinetic energy. So we'll go ahead and plug in our numbers. 1/2 times 3,500 times 5 squared minus 1/2 times 3,500 times 20 squared. That gives us 43,750 minus 700,000. We get negative 656,000 joules. So rounded to 3 sig figs, we get 656,000, and we get a negative because we do decrease our velocity, and you can see that we're going to have a smaller number minus a bigger number, which gives us our negative change in kinetic energy. So in this problem, it says the same 3,500 kilogram car is moving at 5 meters per second. So in the previous problem, we ended moving at 5 meters per second. It says it then stops and moves in reverse at negative 5 meters per second. What's the change in kinetic energy? Well, one thing, if you remember, the direction of the velocity doesn't matter when it comes to kinetic energy. So really 5 meters per second and negative 5 meters per second is actually the same speed. So there's a total change of 0. But we can go ahead and plug in the numbers into the equation. 1/2 times 3,500 times negative 5. Be sure to square that negative, minus 1/2 times 3,500 times 5 squared. We get 43,750 for the final, minus 43,750 for the initial, and we subtract the two and we get 0. Now you may look at this and say, well, it slows down, so doesn't that mean that we lose kinetic energy? Well, it is true that we do lose kinetic energy, but then it speeds back up, which means we gain kinetic energy. Now changing kinetic energy just cares about the final and the initial, so the total change is 0, but that's because that we lost the kinetic energy, then gained the same amount of kinetic energy back to give the total change of 0. So one concept we're going to be talking about, collisions, and momentum is always conserved in collisions, but if kinetic energy is also conserved, meaning there's no change in kinetic energy, so kinetic energy of one thing increases, another thing decreases, but if we add those increases and decreases together, we get a total of 0, then that collision is considered an elastic collision. So every collision with no outside net force momentum is conserved, but if kinetic energy is conserved, then that's considered an elastic collision. Likewise, if we don't have conservation of kinetic energy, then this is considered an inelastic collision. So the only way to really determine whether a collision is elastic or inelastic is whether or not we conserve kinetic energy. If we figure out the total change in kinetic energy, it's equal to zero, it's elastic. If it's not equal to zero, it's considered inelastic. Now in the real world, there's no perfectly elastic collisions ever, because that just doesn't happen, but you can get some that are pretty close. And getting pretty close in comparison to the amount of kinetic energy. If we have a really, really small amount of change in kinetic energy, then we can consider that an elastic collision. To observe a collision, if you look at a collision, one that looks like it's elastic would be ones that bounce off of each other, and then ones that are inelastic are ones that perfectly inelastic, where they stick together completely and move off together. And in between, it's going to be between elastic and inelastic, depending on how much kinetic energy is conserved. So in this problem, it says car 1 is a mass of 1,200 kilograms moving at 25 meters per second, strikes into car 2 with half the mass of car 1 and as it was sitting still. Car 2 then flies off at 30 meters per second while car 1 moves at 10 meters per second. All right, so what we're going to do is we're going to look at the total change in kinetic energy to answer this question at the top: is this collision elastic? So we need to figure out the total change in kinetic energy of the first car. That's 1/2 mass times final velocity squared minus 1/2 mass times initial velocity squared. Go ahead and plug in our numbers. It's going to be 1/2 times 1,200 times 10 squared minus 1/2 times 1,200 times 25 squared. Now, the first car slows down, so we expect a negative change in kinetic energy, which we see with negative 315,000 joules. The second car has a change in kinetic energy, 1/2 mass times final velocity squared minus 1/2 mass times initial velocity squared. Now this one speeds up because it starts at 0 and then ends at 30 meters per second. So we go ahead and plug in our numbers. Half of 600 because car 2 had half the mass of car 1. Half of 600 times 30 squared minus half of 600 times 0 squared, and we get that it's 270,000 joules. So when we add these two changes together, we get a total of negative 45,000. So that means that it's not elastic, because we do have a decrease in kinetic energy. All right, so the work energy theorem, if we look at the amount of work done on the system, then it's going to be equal to the change in kinetic energy. So the total work that is done on a system with a net force for an open system will produce a change in kinetic energy. And what I want to do is I want to show the equation that defines this. So we got the total work done on the system is going to be equal to net force times displacement. Now, something to keep in mind here: the net force, it's not usually something we have in the work equation. A lot of times when we talk about work, we talk about the total, or the work that one force is doing, and that one force times displacement gives me the work for that one force. But if we have multiple forces acting on a system, then to figure out the total work, then we need to take the net force times displacement. Now, to find the total work on the system, you could take each force and multiply by the displacement in order to figure out the work of each one added together, and that'll give you the total work. Or we can do this method, which we're going to be deriving here. So net force, according to Newton's second law, equals mass times acceleration. We'll go ahead and plug that in. And you see here we got mass times acceleration times displacement. Acceleration times displacement has actually shown up in another equation we have of final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. So to get that acceleration times displacement by itself, we need to isolate it, get everything else on the other side, and we're going to plug what we get into this acceleration times displacement. So we subtract initial velocity squared from both sides, and that's going to give us final velocity squared minus initial velocity squared equals 2 times acceleration times displacement. We divide by 2 in order to get that acceleration times displacement on their own, and then we get the final velocity squared minus initial velocity squared divided by 2. So that's going to plug in for our acceleration times displacement, and we get that times mass. And now we're going to distribute the mass inside of the equation. We got to distribute it into the numerator. This 2 we're also going to distribute to each one of these, but it's dividing, so that's the same. Dividing by 2 is the same as multiplying by 1/2. So when we distribute this, what we get is work is going to be equal to this dividing by 2, which is 1/2 times the mass times final velocity squared, minus 1/2, that dividing by 2, times mass times initial velocity squared. So when we plug that in, we get mass with a 1/2 mass times final velocity squared is a final kinetic energy, and 1/2 mass times initial velocity squared is an initial kinetic energy.
So now that we have this equation, we go ahead and plug in that this 1/2 mass times velocity squared, that's going to be equal to kinetic energy. Kinetic energy is 1/2 times mass times velocity squared. And then since we're dealing with final velocity here and initial velocity here, then this part right here, the 1/2 mass times the final velocity squared, and the 1/2 mass times initial velocity squared actually gives me a final kinetic energy and an initial kinetic energy. So the work is going to be equal to the final kinetic energy minus the initial kinetic energy. And then to help us with this equation, we're going to take that initial kinetic energy to the other side, and this is going to be the work energy theorem that we're going to start with. Now this equation is actually going to be the basis for which we build conservation of energy later on, but you can see that with the total kinetic energy that we start with is going to be equal to the total kinetic energy that we end with if we have no work being done. But with the kinetic energy we start with plus the work done is going to increase or decrease our kinetic energy depending on if we do positive or negative work. So in this example, it says a horizontal force of 3,250 newtons is applied to a 110 kilogram mass initially at rest for a horizontal distance of 0.15 meters. What is the final velocity of the mass? All right, so first off, we start with our work energy theorem where we have the initial kinetic energy plus the work is going to be equal to the final kinetic energy. Now each one of these terms has its own equation, so we go ahead and figure out what the equation is for each one. First off, for the initial kinetic energy, it's going to be 0 because it starts at rest. So the initial velocity is at rest, so that means the initial kinetic energy is going to be at rest. The final kinetic energy is going to be equal to 1/2 times mass times the final velocity squared. So we go ahead and plug in what we know, which is just the mass. So that's going to be 1/2 of 110, which gives me 55 times the final velocity squared. And that final velocity is unknown because that's what we're looking for in this equation. The last thing is going to be the work. The work is going to be equal to force times displacement. Now we're given the force. The force is 3,250 newtons. The displacement is 0.15. So when we plug those in, we get that the work done is going to be equal to 487.5 newtons. Or 0.5 joules, I'm sorry. So that gets plugged in, and then we get the work is going to be, the initial kinetic energy is going to be added to 487.5, and that's going to be equal to the 55 times the final velocity squared. So then we divide both sides by the final velocity, or by 55, and then we square root both sides in order to figure out that final velocity, and we get 2.98 meters per second. And that gives us our final velocity for this problem. This next problem, it says that a 100-gram hockey puck is sliding across an ice at 1.3 meters per second. A player exerts a constant 4.5 Newton force to give the puck a velocity of 3.8 meters per second. For what distance did the player apply the force to the puck? All right, so first off, we use our work energy theorem, which is going to be equal to the initial kinetic energy plus work is going to be equal to the final kinetic energy. Now, the initial kinetic energy is equal to 1/2 times mass times the initial velocity squared, but keep in mind the mass is given in grams, so we have to convert that to kilograms. To convert that to kilograms, we divide by 1,000. So that gives us 1/2 of 0.1 times 1.3 squared, and then we plug that in, we get 0.0845 for our initial kinetic energy. For the final kinetic energy, it's going to be equal to 1/2 times the mass times the final velocity squared, which is 3.8 squared. That gives me 0.722. And then our work is going to be equal to the force times displacement. It says the force is 4.5 newtons. The displacement is unknown. That's actually what we're looking for. So we go ahead and plug each one of these into our equation. We get the 0.0845 for our initial kinetic energy, the 4.5 times displacement, that's our work done, and then the 0.722 for our final kinetic energy. All right, so we take that 0.0845 to the other side, subtract those two, and we get a total of 0.6375 on that side. And then to find our displacement, we have to divide by the 4.5, and that gives us a total displacement of 0.142 meters, which is about 14 centimeters for the distance that the force was being applied.